Hey guys, Miss Peterson here. Here to talk to you about building galvanic, aka voltaic cells, calculating their cell potential, and relating that to Gibbs free energy. Okay, so we're going to really talk about what is going on in these electrochemical cells, aka batteries that we can create. What you have to understand about this is that each cell has a standard reduction potential. Okay, and that's based on the half reaction. Remember, in electrochemistry, we're always talking about the reduction half and the oxidation half. Okay, that potential is measured against the standard, which is a hydrogen electrode, basically an inert piece of platinum bathed in hydrogen gas that doesn't really react. We assign that a voltage of 0, just like how we assign other things in chemistry, like the mass of a carbon-12 atom is 12. Okay. So, those standard reduction potentials, you're going to use this handy-dandy chart for. Okay, you'll see lots of these types of charts, but they're standard reduction potentials. So on this chart, all you have is the reduction, and it's standard. So that means it's at standard conditions. Now, an important thing to note about standard conditions, important thing to note, standard conditions is not STP, okay? It's not standard temperature and pressure. Why? Because guess what? Standard temperature is 0 degrees Celsius, aka really, really, really cold. We don't like doing things at 0 degrees Celsius. So instead we have standard conditions, which is at a comfortable 25 degrees Celsius, okay? And standard conditions also means that we use 1 molar for our solutions. Why? Because it makes calculations easy. Okay, 1 molar. And, you know, that little knot, the little 0 degree sign or whatever you want to call it, okay, that's what we use to indicate standard conditions. And you'll see that everywhere. Typically, I'll use E-cell because that's what I have always used, but EMF and the little weird swirly E mean the exact same things, okay? But we're focusing on it at standard conditions. So let's go ahead and take a closer look at this diagram of a circuit or of a galvanic cell conducted from sulfate and copper, okay, using those metals as the solution, okay? So let me zoom in over here on that. Okay. So we have our anode. Okay. Our anode is a zinc anode. Okay. And then you've got your zinc 2+ ions in solution. Okay. So at our anode, we are turning zinc into zinc 2+. Okay. Zinc solid, going to zinc 2+, and we have to bounce out the charge, so 2 electrons. Electrons are being removed from that zinc. So is that oxidation or reduction? Well, if you remember oil rig, oxidation is loss. Okay, anode, this is our oxidation. Okay, also remember N-ox, anode, oxidation. We're over at the cathode, we have a red cat. Reduction. What reduction is gain of electrons? What is gaining electrons? Copper. Okay, so we have our copper 2+ ions gaining 2 electrons to form our copper solid. Okay, so that is what's going on in this solution. Okay, the electrons are flowing. We probably have, this is our porous disk through which those sulfite ions can migrate, okay, in order to keep that charge balanced and neutral. Okay, if we looked at it down here, oops, sorry, let me clear the ink before I do that. Okay, you can see those half reactions happening. The zinc is losing electrons, forming the zinc ions, which are going to get dissolved into solution, okay, where the copper is gaining those electrons, causing the copper 2+ ions to plate onto the solution. So if you were actually doing this experiment, you would see the copper anode getting bigger and the zinc anode kind of shrinking or dissolving in solution. Okay, and this reaction produces 1.10 volts of electricity. So how do we construct one of these cells? Okay, well, it depends on what's available, okay, and how do we know what's going to be oxidized and what's going to be reduced and how much voltage? We're going to get to all of that, okay? And to do that, we will need our table of standard electrode potentials, okay? Here is something that you really, really need to know. The most positive reduction potentials are easily reduced, okay? The ones that are more positive are more reduced. On the chart, okay, on the chart, you can kind of see it as whichever one is higher up here, okay, more positive means more, oops, that's not right, more likely to be reduced, okay? So the ones at the top, more likely to be reduced. The ones at the bottom, more likely to be oxidized, okay? And it'll depend on kind of what kind of cell that we're constructing about. It might be one from up here and one from down here, or it might be two that are kind of close to each other. It just depends. On the actual AP Chemistry exam, they don't give you this chart. They'll just give you like one segment or something of it that you'll need, okay? And we'll see examples like that. So moving right on along. Okay, so when we're calculating these, we're always going to calculate the cathode minus the anode, or in a different way, the reduction minus the oxidation. And you'll see when I do these, I just tend to flip it there. But it's always reduction and oxidation. Okay? Always remember, metal with the more positive reduction potential gets reduced. Okay, more positive, the bigger number. Okay, not necessarily bigger in magnitude, but like the actual bigger number, like on a number line. So let's look at an example here. Consider the galvanic cell based on the reaction. Aluminum 3 and magnesium solid reacts to form aluminum solid and magnesium 2+. Give the balanced cell reaction. Calculate E naught for the cell. Okay, so first we got to figure out who's being oxidized and who's being reduced. Okay, so first let's look at the aluminum. Okay, we have aluminum 3+ turning into aluminum solid. Well, in order to do that, it must have gained electrons to get rid of that positive charge. How many? Well, 3 of them. Okay, 3 electrons. So it got reduced. Okay, oil rig. Reduction is gain of electrons. Okay, so this is our reduction. If you remember our red cat, this is what would happen at the cathode. Okay, now we go to our handy-dandy little chart here, and we find the aluminum. These are all written as reduction, so this is exactly how it looks in the chart. So we're looking for that reaction, and you see it's about 2/3 of the way down the page. Okay, but the cell potential for this is at negative 1.66 volts. Okay, so now let's look at the magnesium. Okay, the magnesium is going from a solid to electrons. It is losing electrons, therefore it is oxidized. Okay, so let's look at the oxidation. Okay, that'll occur at our anode. Okay, so we have magnesium solid turning into magnesium 2+, and to do that it must have gained 2 electrons. Okay, now remember on our chart, these are all written as reduction, so we're actually going to see the reverse of this reaction. Okay, so let me go ahead and find that. Look at the chart, look at the chart. There it is, it's 2 beneath the aluminum. Magnesium 2+ plus 2 electrons goes to magnesium solid. And it's on the chart as a negative 2.37. But We flipped the reaction, so what do? We flip the charge. So it's going to be positive 2.37 volts. Okay, cool? Okay, cool. Now, to get the energy of our cell, you just add them up, and that makes it easier. We already flipped the standard reduction of the oxidation, so instead you just, add them up. And when you add those up, the E naught of the cell is negative 1.66 plus 2.37, which is 0.71 volts. Woohoo! We got it right. Okay, cool? Okay, cool. But we are not done yet. They want the balanced cell reaction, so the whole reaction that's going on. In order to do that, we have to flip some signs here and make sure these electrons cancel out, because we don't write reactions in overall cells. So, let's see. We have 2 electrons here and 3 electrons here, so we're going to have to make that 6 electrons, which means we're going to have to times this whole thing by 2 and this whole thing by 3. So we have 2 aluminum, 6 electrons, 2 aluminum solids. This one got times by 3, so 3, 3, and 6. Then our electrons can cancel out, so that our overall reaction for this guy is 2 Al3 plus 3 magnesium solids form 2 aluminum solids plus 3 Mg2+. Okay, and then you can see we have 2 3+ ions, so a total of 6 positive charge on this side of the reaction, 3 2+ is a total of 6 positive charge on this reaction. Okay, we have 6 electrons involved in this reaction. That'll be important later. Okay, but you can kind of see how that whole thing works out. Okay, does that make sense? Yes, yes. No, we didn't really do anything with the voltages because they are actually happening separate. You just use the voltages as they are in the table. Okay, and then you balance the reaction afterward. Okay, cool? Okay, cool. Let's look at another example. A galvanic cell is based on this reaction. Ooh, that's a doozy. Okay, and they give us the standard reduction potentials. This is kind of how it would look on your AP test, okay, where they just give you the cell potentials, but then you have to recognize which one's going to be reduced and which one's going to be oxidized. So first, let's figure out which one of these is more positive. Which one's the higher number? Well, 1.51. So this one is going to be reduced, okay, which means that the other one, okay, is going to be oxidized. So we are going to have to kind of flip this reaction and flip the sign there. Okay, I'll write that again and write it under, but first let's just calculate the E cell. Okay, by adding up those two things, we have negative 151 minus 1.20. I can do that in my head. Our E cell is 0.31 volts. Yep, it's always going to be positive, okay? If it's not positive, you don't have a battery. That you did something wrong, okay? Now, let's figure out this whole reaction. That's going to get a little bit messier because notice I have 2 electrons here and 5 electrons here. I need to flip this reaction, so I'm just going to rewrite the whole thing, okay? First, let me write the top one, the reducing one, so we just leave it written as is. MnO4 minus plus 8 hydrogen ions plus 5 electrons forms Mn2 plus 4 waters. Okay, now let's write the other one, and I'm going to flip it, okay, because it's being oxidized, so I'm going to flip the reaction. So the products become reactants. Now I have ClO3 minus plus H2O going to ClO4 minus plus 2H plus 2E minus. Okay, now we need to balance these. And the only way to balance it is going to be with 10 electrons. So I'm going to times this top one by 2. So this becomes 2. This becomes 16. This becomes 10. And then I have a 2 there, and this becomes an 8. Okay, this one, okay, the second one, it has 2 electrons. So I'm going to have to multiply it by 5. Okay, so I get a 5 there, a 5 there, a 5 there, a 10 there, and a 10 there. Okie dokie. Now let's clean this up a bit because it's a bit of a mess. Okay, so 10 electrons and 10 electrons cancel out. Okay, I have 10 H pluses right here and 16 H pluses right there, so I can cancel out 10 of them and make it so this is just 6 now. Okay, and then I have 8 waters and 5 waters, so these 5 all cancel out, and this becomes a 3. Whew, is that all I can do? Yes. So that my final reaction then is 2, come on, you can do this, 2 MnO4 minus plus 5 ClO3 minus forms 2 Mn2 plus 5 ClO4 minus plus 3 H2Os. Oopsies, I forgot my H pluses. Hold on, let me just rewrite the reactants again. 2 MnO4 minuses plus 6 H pluses plus 5 ClO3 minuses. Okay, sorry, my pen's acting up a little bit in this corner, but you get the general idea. Okay, so there's our overall reaction. Okay, cool. Okay, cool. Let's do another one. Okay. The standard cell lead acid battery operates with the following half reactions. Okay, we got our anode reaction and our cathode reaction, and then our overall reaction. They actually give us the E cell for the overall reaction. We have to determine the reduction potential for the anode. Okay, I want you guys to go ahead and try this one on your own first. Okay, and then look at the answer. Okay, so we got our E cell. Okay, which one of these is going to be oxidized? Well, we can tell. Okay, we actually can't tell. Okay, we're just going to use the formula. Okay, E cell equals E anode minus E cathode. Nope, sorry, backwards. E cathode minus E anode, aka reduction minus oxidation. Okay, so we have 2.041 equals my cathode, which is 1.685, minus my reduction one, or minus my anode, my oxidation, E anode, and then we minus out and solve, minus 1.685, minus 1.685, okay, and you get 2.041 minus 1.685 gives you 0.36. 0.356 equals negative E anode. Okay, so E anode, change that to a positive, make that one a negative, and we get 0.356. volts. The standard reduction potential for lead. That makes sense. Okay, cool. Oh, negative. Sorry. Cool. Okay, cool. Okay. Now we're gonna do some drawing. This is gonna be hard, but we got this. Calculate the cell voltage for a galvanic cell that would utilize silver metal. Okay, so we know we got some Ag in there and some iron 2 plus and iron 3 plus ions. Draw a diagram of the galvanic cell for the reaction. Label it completely. Hint, when are inert electrodes necessary? Okay. So inert electrodes are necessary when you don't want the metal to be involved, when you're just going from one ion to another ion, such as the case with the Fe2 plus and Fe3 plus. So let's go ahead and figure out the reactions that are involved here. Okay, so I'm going to do these, try to do them like off to the side because we're going to actually draw the picture in like the main space here. Okay, so first RAG. Okay, let's go to the handy dandy table and find the one involving our silver solid. Okay, there it is, right up top somewhere we have Ag plus an electron forming a G solid. Okay, the standard reduction potential for that one is 0.80 volts. Okay, now let's find one involving Fe and Fe3 plus. Nope, there's Fe to Fe solid, which is definitely a possibility, but we want both of these ions involved. So we want the Fe to just Fe3 plus. Where is it on the chart? Where is it on the chart? Okay, there it is. It's about a fourth of the way down the chart, where we have Fe3 plus. Again, I'm just copying these directly from the chart. Goes to Fe3 plus. Oops, sorry, Fe2 plus. Fe3 plus one electron gives you Fe2 plus. And the standard reduction potential on that one is 0.77 volts. Okay, so from that we can tell who's going to be reduced. Well, the one with the more positive, the higher reduction potential. Okay, so that's going to be the silver. Okay, the silver is going to be our reduced, okay, where this one is going to be oxidized. Okay, so we would flip this reaction. Okay, let me just show you what's going to go on there. Let's flip this reaction, which means we're going to flip the sign here. Okay, so now we have Fe3 plus going to, nope, I lied. Okay, I can write things backwards. Fe2 plus going to Fe3 plus an electron. Okay, so now we have our reduction and our oxidation. So our total E cell is going to be 0.03 volts. AKA, this is not a very good battery. Okay, that's a tiny amount of voltage. To put that in perspective, a standard AA battery gives you 1.5 volts. Okay, but let's go ahead and kind of draw this and picture what is going on here. Okay, so we draw our two beakers for our half reactions. Okay, I have a dead spot there, but it's fine. Okay, we have our two electrodes. We got our solution. We have our wire connecting them. This is our voltmeter. And then don't forget always about the salt bridge. Or our porous disc, whichever we chose to use. Okay, I'm going to clean that up a little bit. So that you guys get a better picture here. Okay, there we go. That is our standard thing, I guess you would say. Now we have to add in all of our information, okay? It doesn't matter which side you put the anode on and which side you put the cathode on. It doesn't matter. Picture this like sitting on your desk. depending on which way you look at it, one's going to be one, one's going to be the other. So let's go ahead. I'm going to put our silver on the left side because that's the one that I wrote on top. So I'm going to put my Ag solid here. Okay, now that is a reduction. If you remember a red cat, okay, this is going to be red cat, my cathode. Okay, so this one must be my anode. And at my anode, I just have iron turning into other iron, not iron solid. So that's when we need an inert cell or inert metal like platinum. Okay, platinum is our go-to. Remember, platinum is a standard one that we got going on here. Okay, now electrons flow from the ion to the cathode. It's a fat cat. Anode to cathode, fat cat. Yeah, fat cat. Okay, so I'll draw my little electrons in green, and they are going this way. Okay. And how much electrons? Well, 0.03 volts of electrons. Okay, now let's look a little deeper at what's actually going on in the solutions that are here. Okay, so in our platinum we have our Fe2+ ions. Oh, and our Fe3+ ions. Okay. And then when we'll draw 5 of them, okay? How many of them? Well, we have a 1.0 molar solution of them, okay? Of both of these, because, standard conditions. And I can't write over on this side, so I'm going to have to write it. I have a dead spot. Okay, but the other one is also 1.0 molar, okay? Now, every time that you lose an electron from that, you take an electron from that Fe2+, it becomes a 3+. Okay, so you can see how you'll have both of those in solution. Where on the other one, okay, we got our Ag solid, and it's gaining electrons. So what'll happen there is we'll have our Ag+ ions in solution. There's electrons gathering up here, so they're going to form, okay, some more Ag solid there. For every one electron, you get one more piece of Ag solid. Okay. Now let's talk a little bit about what's going on in the salt bridge. Okay, our salt bridges are typically K ions and NO3- ions because both of those things always dissolve in solution. They're not actually reacting. But in this one, because we are on the cathode side, we are removing positive charge. So our NO3 is going to be coming in to fix that. Okay, we're on the other side, okay, you are removing electrons, okay, making it, I am backwards here, okay, on the left side, on the cathode side, you are taking away those positive charges, giving it a slightly negative charge, so you're actually going to have the K+ flowing in there, and on the other side, you will have the NO3- flowing, okay, because you're removing electrons, so it's going to get to be really positive, so those negative nitrate ions are attracted into it, okay, until you run out of ions, aka you got a dead battery. Okay, cool? Okay, cool. Now, let's talk a little bit about the electrical work, okay, and free energy. We need to connect this electrochemistry to thermo and equilibrium, okay? The sign of E cell is important in determining whether it's spontaneous. A positive E cell means like, yeah, this reaction's gonna happen, okay? The electrons will spontaneously flow and present voltage. Negative means it's not spontaneous. You're gonna have to put electrons in to make it go. If your E cell is 0, well, then no electrons are flowing. You got a dead battery. It's at equilibrium. Okay, so we can connect that to Gibbs free energy, the amount of energy available to do work, and that is all summarized in this handy-dandy little chart. Okay, Z is 0, delta G is 0, it's at equilibrium. Nothing's going to happen. Okay, this is your dead battery. Okay, when E cell is positive, delta G is negative, K is greater than 1. That means electrons flow. Okay, it is spontaneous. Where we'll talk about this when we get to electrolysis. If delta E is negative and delta G is positive, this is not spontaneous. Okay, aka if we want that to happen, we're going to have to put electrons in order to make it go. Okay. So we'll talk about work, okay, which is EMF or the cell potential, aka the voltage. Okay, voltage is the energy and the charge. Okay, the unit for that is the volt. You might remember that from physics class if you took physics. And by definition, it is 1 joule of energy to transfer 1 coulomb of electric charge. Okay, so we don't typically work in coulombs because coulombs are like really, really, really small. That is the like fundamental. It's basically a really, really small number. It's not very convenient to work in. So instead, we multiply the Faraday's constant by the number of moles of electron. Faraday's constant is the charge per mole of electron. Okay, and we can use this, okay, where n is the number of moles of electrons, to relate E, our standard electron, to delta G, our amount of energy available to do work. Okay, and that is the negative nuff equation. Okay, another delta G equation that's going to pop up over and over, but it's negative G equals negative N, aka the number of electrons. Remember, I told you earlier that was going to be important. F, which is Faraday's constant. Sometimes you will also see this written as 9.65 times 10 to the 4th. That is the same number, just in scientific notation and not in scientific notation. Okay, and E naught, that is our cell potential. Okay, aka the thing that we've been calculating in all of the previous example problems. And it's negative to keep that convention of a positive E cell is favorable and spontaneous, but it's a negative delta G that's favorable and spontaneous. Okay, so let's practice using this equation with a couple of examples. We've already seen this equation. Shouldn't look familiar, but it's another relationship between delta G and K. We're going to put those together in a little bit to relate K and our E cell. Okay, number 5. Using the table of standard reduction potentials, this one, calculate delta G for the reaction. Copper 2 plus Fe solid goes to copper solid and Fe2 plus. So first, let's go ahead. Oh, and then we have to predict whether or not it's thermodynamically favorable. That'll be fun. Okay, so let's go ahead and figure out our half reactions going on here. We have our copper 2 plus turning into copper solid, so it must be gaining electrons. Copper 2 plus 2 electrons turning into copper solid. That is a reduction, okay, because it's gaining electrons. Okay, reduction. Okay, and then our Fe is losing some electrons to become a positive charge, so that's our oxidation. Don't forget oil rig. Oxidation is loss, reduction is gain. Okay, so we have our Fe solid turning into Fe2 plus, and then it must have 2 electrons there. We use our handy-dandy table to look up these values. Okay, copper 2 plus 2 electrons. Okay, that one has a value of 0.34. Okay, iron solid. Okay, remember this one is the reverse of how it's written in the table. So I'm going to flip the sign. Okay, it should be 0.44 4, it's negative on the table, so it is positive here. Okay, so then when we add those up, we get our E cell of 0.78 volts. Okay, now it wants to know if this reaction is thermodynamically favorable. I'm guessing yes, because it has positive E cell. But let's go ahead and plug it into our equation and figure out, calculate the delta G for that reaction. So delta G equals negative nuff. And again, this is on your equation sheet. It's not one you have to memorize. What is our N here? Well, it's easy. We got 2 here, 2 here. So our N is 2. So delta G equals negative 2 times Faraday's constant, which we just gave you. It is 9,000. Sorry, I'm going to do this real quick and it's going to be annoying. 96,500 coulombs. And my computer's dying. Coulombs per mole. How many moles? 2 moles. Times our E cell, 0.78. We plug that into our calculator. Negative 2 times 96500 times 0.78. And you get negative 150,540. Okay, which I would round and convert to kilojoules, so negative 151 kilojoules. Okay, but again, when I plugged it into my calculator, negative 150,540, and that will be in joules because Faraday's constant is in joules. Okay, cool. Oh, so that means yes, negative delta G. It is thermodynamically favorable. Yes. Okay, cool. Okay, cool. One more example. Right? Yeah. Yep, one more example going on here. Using the table of standard reduction potentials, predict whether 1 molar HNO3 will dissolve gold metal to form a 1 molar gold 3+ solution. Okay, so it's talking about turning gold solid into Au3+ and 3 electrons, okay, dissolving the gold. The standard reduction potential for that is 1.50. Okay. So that means if something were to make that happen, okay, were to drive this reaction, it would have to lose electrons, so it would have to be oxidized. So we would need a standard reduction potential that is more positive than that. And if you look on this table, there are only 2 standard reduction potentials that are more positive than that. However, neither of them are nitric acid. Okay. And if we look on our chart, we actually don't have anything related to nitric acid there. So if I needed it, I would Google it. Oops. Nitric acid standard reduction potential. It would be given to you on any test or anything. I just wanted to show you. Okay, there they give me the reaction, and its E naught is 0.96. Okay, so let me go back and write that. It's NO3 minus, because nitric acid is a strong acid, so it'll dissociate completely into nitrogen ions. So we have NO3 minus, 4H plus 3 minus. NO3 minus plus 4H plus 3E minus, forming NO and 2H2O. So nitrogen monoxide and 3 waters. And the standard reduction potential of that was 0.96. Okay, therefore it is not more positive. Okay, so it would be the one that is oxidized and the aluminum would get reduced. Okay, therefore it would not dissolve. Okay, so because this one on his table of standard reduction potentials is more positive. But I think that actually might have been a little confusing the way I wrote it, so I'm just going to actually get rid of that negative sign and actually write this as a reduction so you guys can see what I mean. Okay, so that one is more positive. It is the one that would be reduced, not oxidized. Okay. So we would say the gold, sorry, and I put U, AU has a more positive standard reduction potential. So it will be reduced, not oxidized into an ion. Okay, cool. Okay, cool. So next you guys do have this little self-check. I want you guys to do that on your own, and we will talk about it in class.